Hi folks, so I'm Digvijay and we are building this startup called Contrails AI. I think one of the very few AI startups out of India in this particular theme. And some of the people are actually here at the factory, etc. So basically the mission is build AI solutions to empower online safety. A lot of people here essentially come from the domain side of things, etc. But there's a lot of platform level organization, tooling, arming that is also required. So that some kind of whatever social media platforms are out there, they can also use AI technologies to sort of do things cheaply, etc., etc. They have their own constraints. So I'm Digvijay. I have been doing AI computer vision for the last 12 years broadly. Have been an engineer, researcher, product manager, and now as a founder of Contrails AI as well. And with me, we are 3 full-time people, out of which 2 come from this company called Hyperverse, which is India's leading financial fraud and KYC customer onboarding sort of thing. So we know what we are building over here. So just disclaimer: the slides are going to be a bit technical, but I'll try to skim through it and just try to communicate what essentially goes behind building these kind of sophisticated detection methods and technologies. So first of all, what is synthetic media? Maybe some kind of a heads up, so to say. So there has been a history of deepfakes or maybe sort of impersonation attacks people have been doing on image and audio side, right from Photoshop-based face edits to then face swap related technology sort of coming up in 2017-18. I think one of the first videos was this thing called Project Obama in University of Washington, and Obama's videos are floating quite a lot. And then we started seeing the origination of lip sync attacks. So here you did not have to swap faces on top of people, but you could make people speak something which they had not, right? So again, an impersonation attack. Then more recently, we are starting to see a lot of audio-only attacks because if it is only single modality, it is very, very hard to sort of narrow it down to, why is this a fake, etc. Then there are face reanimation. So what people are doing, they're just feeding it a portrait video or portrait image of people and then give like some kind of audio tokens and it starts speaking that, right? So this is very, very different from everything else which we previously saw. And more recently, we are seeing these AI-generated extended videos. It's sort of like next token prediction, but in a video and audio modality side rather than text tokens. So yeah, and I think we will see even more sort of generation methodologies in the future. A lot of VC money and in general capital flowing into the generative AI side of things. When it comes to detection, what are the main problems? So we've tried to summarize it into sort of 4 main points. First is that it's a constantly evolving goalpost, which means detection also needs to keep on catching up to that. Second point is basically the real world deepfakes and manipulated media which we see is not at all even close to what research data sets are out there or research kind of settings which are out there. So to be able to build strong detections, we have to ensure that this difference is basically taken care of. Then a lot of the ways these deepfakes are created, reverse engineering that process is very, very important. So for that we have to understand how is it being generated? Is it a diffusion process? Is it a GAN process? Is it a auto-encode kind of a process? And then there are a lot of nuanced ways people are attacking. For example, they mix audio-only attacks is one. Sometimes people do Photoshop plus deepfake and so on and so forth. So there is a various kind of ways people are also creating this. So coming from a detection standpoint, basically our solution needs to have 2 very, very strong performance levers. One is that it needs to work in the real world setting. So real world robustness, extremely, extremely important. So where does it essentially fail? When people upload it on social media platforms here and there are a lot of compression, a lot of transmission related artifacts which also sort of come into play and sort of become part of the media file. This is not there in the research data set. And then need to make sure that the facial profile, the ethnicity, all the other kind of nuances are also taken care of. The second most important objective is to be able to generalize across unseen attacks. So let's say we have a universal, very, very strong synthetic media detection algorithm. It should be able to work in any kind of future deepfake creation algorithms that are yet to come even. So with these kind of sort of principles in mind, basically an AI lifecycle or AI pipeline can be divided into data work, into what kind of architectures are you going to use, which is going to bring out those sort of data points or manipulation signals more and more. Some kind of ensembling, I'll come to this later. And then how do you make sure that it basically works at scale? A lot of people can use it, on a daily basis, and so on and so forth. So on the data side, just two very small points. First is like doing some kind of like data augmentations on the frame level. So what we do is something called a pseudo fake. So we'll have like eye crops, lip crops, and so on and so forth, and we'll just keep on imposing it on new and new images and create a lot of synthetic data. So this is number one. And number two is when the AI model is sort of taking the image forward, there's a latent level representation of that same information. This is sort of like an embedding layer, as we call it. And then do a lot of latent space augmentation. So where it helps is, it basically helps us with a lot of adversarial attacks. So for example, people might change just few pixels here and there, and it might change the prediction of the output drastically, right? So in order to make it robust to that, there is a lot of work that goes on over here as well. So one very simple insight is, let's say it's a deepfake, sort of like a face or a lip sync. The exact pixels where it's gonna create that manipulation is around the face region. So there is a localization or hot region where essentially you should be looking, and you can detect the deepfake signal slightly better. So yeah, one thing I'll say about this slide is basically what we do is, given a video is a sequence of frames, what we do is we will split each image, each frame in the video into patches, because only few patches in the video have the deepfake signal, not the background patches. Second feature is the temporal information. So basically it takes set of frames together rather than going one frame at a time. The third element is we also convert the images into something called as frequency transformation. This is Fourier transformation, second, third order. This essentially brings out the AI signals even more, right, from the image pixel side of things. And then at the end of it, we have something called as consistency modeling, where we sort of take the spatial feature, frequency feature, temporal, face region, and do loss computation, basically do model training using all of these combination of features. So that was just video deepfake. For audio spoof detection, there is a totally different set of methods, totally different set of algorithms that you have to build. So this just simply summarizes that in audio, the most important features are the linguistics feature and the style and the tonality kind of features. And the model is essentially taking care of that. There are separate parts of the model that take care of both elements, and you have something better essentially. So let's not look at this. So what this slide essentially is talking about, like transformers, which is the latest architecture, has inherent problem when we do deepfake detection using transformers backbone, which is highlighted over here. So basically, the token-based training which transformers do is it's not actually aligned to how synthetic media manipulation detection works, because they are looking at the full image in one go. So basically this encoder is looking at all patches in one go and trying to make a prediction. Whereas if we do it like token-based supervision, we can say, hey, this patch is fake, this patch is real, this patch is fake, and so on. So this, we need to break the transformer at this stage and do like separate training for the first part of the model. So this is something which is under research. We are developing a different algorithm to be able to do that. So there was this challenge called Defactified. It's a AI conference, tier 1 AI conference challenge and so on. So we won this challenge, and the task was to detect images between real versus all kind of AI generated images. So yeah, this is sort of the system diagram of what we ended up using. It's basically a mixture of bunch of architectures which are sort of using the frequency information plus a lot of Sven transformer based something. So if anybody wants to know more about this, maybe after this session we can cover it. And finally, when we have multiple models, so let's say we do video deepfake detection using 3 to 4 different kind of methods, how do you merge them together? So there are two ways to merge it. One is a low level feature ensembling. So here it's looking at the input information of the image and trying to determine, hey, this downstream model to use from there on. And the second thing is attack type. So if it can we make the ensemble learn whether it's a face swap, whether it's a lip sync, and it is automatically detecting which model to run in the downstream side. So I'll skip this. So final slide. Basically, this is the tool which we have built, and I can see some people who might have also used this tool out there. So we had to ensure that we take care of all the input types are handled. We create some kind of alert notification system. In the back end, it's running multiple AI models and so on. The most important part is, I think, this visualization or explainability part, where, let's say, given a particular video, we are able to give like a consolidated output. We are able to give like mean scores of those outputs, as well as like localized outputs of across the whole timeline. Yeah, it's done only. So.